Now, in our last problem, given the same curve, we want to find where the tangent line is horizontal. So the idea here is to find where the derivative is equal to 0. So recall we have found previously an expression for y prime, which is this, 2y minus 3x squared over 2y minus 2x. And we want to find where this is 0, so which means that we want to find where this ratio is equal to 0, and a ratio will only be equal to 0 if its numerator is 0. So we need to solve 0 equals 2y minus 3y squared. Now we need to be careful here because we don't want the numerator and the denominator to be 0 at the same time, because in that case the ratio would be undefined. So whatever point or value that we get in the end, we want to make sure that 2y minus 2x is not 0 in the end. So that's the same thing as saying that y is not equal to x. So let's keep that in mind when we're going to look at our answer. Solving for y, this equation, we get that 2y is 3x squared, so y is 3x squared over 2. So that means that any point where the tangent line is horizontal has a y-coordinate, which is 3x squared over 2. So 3 times the x-coordinate squared over 2. So we can use that expression here, the expression y equals 3x squared over 2, and replace y in the equation of the implicit curve to get an equation for x only. If we replace y equals 3x squared over 2 in the equation of the implicit curve, we get x cubed plus y squared. Now y squared is 3 squared, which is 9, times x squared squared, that's x to the 4, over 2 squared, which is 4, minus 2x times y, which is 3x squared over 2. So we can see that the 2's will cancel out. We get this. X cubed minus 3x cubed simplifies to minus 2x cubed, and I brought the constant 2 on the left hand side so that everything is equal to 0. The advantage of doing this is that I will find the x values by finding the roots of the function on the left hand side, which is a polynomial. I chose to remove the 4 in the denominator in the first term by multiplying everything by 4. So therefore I get this expression. I don't expect that you'll be able to find the x analytically. In fact, here it would be quite difficult. In some specific cases, it might be possible. For instance, if you would have had a quadratic polynomial here, you could have applied the quadratic formula. But here it's a polynomial of degree 4. There are formulas that are very, very complicated. In general, if the power is of the polynomial is 5 or above, there are no formulas anymore. So we have to rely on the computer. So here we're going to use GeoGebra to find the roots of this polynomial. So using GeoGebra, I have graphed the function f of x equals 9x4 minus 8x cubed minus 8. And I want to use GeoGebra to find the roots of that function so that I can solve f of x equals 0. So there is a root command that I can use. So you just type root with a capital R, square brackets, and in the square brackets you can put simply f, your function, and type enter, and GeoGebra is really good. It finds the two roots which are minus 0.80637 approximately. So it's giving values rounded off to the nearest fifth decimal, and 1.29664, which is the other point. With the solutions x equals minus 0.8064 and x equals 1.2967, we can obtain the y-coordinates by plugging those values in the equation y equals 3x squared over 2. And therefore we get the 2 points where the tangent line is horizontal on the implicit curve. Notice that the x and y coordinates in both cases are not equal, and that was a condition we had to watch out for, because in the expression for the derivative of the implicit curve, there was a 2y minus 2x, or the other way around, in the denominator, and that meant that we didn't want a solution with x equals y, and that's not the case here. So we're guaranteed that the tangent line is horizontal at these 2 points. And if we graph these 2 points on the implicit curve and draw their tangent lines, we can see that they are completely horizontal, which shows that we found the right solutions. Thank you for watching.